Bismillahirrahmanirrahim. So today we are going to discuss how this probability theory is used in the real world, and the organization of material here is currently not available anywhere else. So we are going to use a approach which is new. So basically the issue is one of trying to find out when an event is a common event, a normal event, and when it is an unusual event. This is the key idea, that is the whole purpose of this lecture. So for example, if I have a coin and I flip it 10 times and it's unbiased like most coins are, then if we get 5 heads and 5 tails, that's fine, that's normal. But if I get 10 heads, that's pretty unusual. I don't expect to see that, so that's an unusual event. So if I get 10 heads, then I will start to doubt the null hypothesis that the coin is fair. And then, you see, this is again one part which is not done in conventional statistics courses. Then I have to go and look why this unusual event happened. Is there something wrong with the coin? If there is something wrong with the way that I am flipping it, sometimes there might be a magnet under the table which is attracting some, and the coin is magnetized, so it always lands in a certain way. So there can be many explanations. So when we reject the null hypothesis, then anything is possible, and we don't know why the null hypothesis was rejected. But we can reject it. And one thing is clear when you have 10 heads, that something is wrong. Well, even that's not 100% clear. Yani sometimes by accident you can get 10 heads. So the whole idea when we start making inference in probability theory in statistics is that everything is judgment. Some judgments are strong, some are weak, some decisions are very strongly evidence-based, some are weakly based, but we don't have certainty at any point. We cannot be 100% sure of anything. So basically it's judgment and experience, and it's qualitative. Even though it looks like there are numbers, and we will use numerical rules, but still the basic idea is qualitative, it's not quantitative. So now the issue is, suppose, as I said, 10 heads is unusual. This is an intuitive idea. How can we calculate and show that this is unusual? And then what if we get 9 heads and 1 tail? This is also pretty unusual. And what if we get 8 heads? Well, that's also unusual, but at what point should we start deciding that something is wrong and we should investigate? So that's called the critical value. At the number, the point at which we say, okay, something is wrong, that's called the critical value. So how do we determine this critical value? This is one of the main goals of this lecture. So, okay, I'm just going to give you the rule for determining the critical value, and then we'll discuss where this rule comes from a little bit later on. So, suppose I have a random variable and it has a range of values. So, then there are some values which we call the central values, and then there are the extreme values. The extreme values can be at the bottom and at the top. So, basically the rule of thumb we will use is that central 95% of the values are the central values, 2.5% at the bottom are extreme values on the bottom side, 2.5% at the top are extreme values on the upper side. So basically 2.5% and 2.5% adds to 5%, that's 1 in 20. So if you think about it in terms of observations, if you have 40 observations, then the one at the top is unusual high, and the one at the bottom is unusually low, and all of the middle 38 are okay. This is the rule that we are going to use to classify central values and unusual values. So now we put this into action. Before we just consider 10 flips of an unbiased coin, and here is the chart of the probabilities. The probability of 0 heads is actually 1 divided by 1024, which is 0.001, approximately 1 in 1,000. Probability of 1 head is 1%. These are the binomial disk probabilities, so they are individual probabilities. Actually, what we need for this decision is the cumulative probabilities, and we'll use those later. But right now I've just put the individual probabilities. So if we use the 2.5% rule, then the combined probability of 0 and 1 is 1.1%. It's still less than 2.1%. So according to the 2.5% rule, both 0 and 1 are unusual values, but 2 is not, because when you get up to 2, then when you add up the probabilities of 0, 1 and 2, this becomes 5.5%, which is much more than 2.5%. So 0 and 1 are unusual, 2 is not. The critical value will be between 1 and 2. This is called the lower critical value. This distribution is symmetric, so basically the upper critical value is between 8 and 9, and 9 and 10 are unusual values. So what we decide from this is that the central values are from 2 to 8. So if you get 2 heads up to 8 heads, then you have no evidence against the null hypothesis of fair coin. If you get only 1 head or 0 heads or 9 heads or 10 heads, these are the 4 events in which you start to suspect the null hypothesis. Okay, so now we have just discussed the critical values. So this I have explained that for any random variables, the median, the mean, the mode, these are all central values, and these are the ones that you expect to see the most often. And then you take a range around this mean, and those are the central values. Those are the ones that you will most often see. And then you take the very extreme values, the ones that are farthest from the center, and you say, okay, those are the extreme values. And if you find some extreme values, then you begin to doubt that the null hypothesis is true, because those are very unlikely under the null. And so the rule of thumb that we have said is that 2.5% is the cutoff. But 2.5% is just a rule of thumb. Sometimes the value that you see is so unusual that it has probability 1 in trillion, and then you have more strong evidence. So the evidence is not it's not that 2.5% is a cutoff, is a sharp cutoff, where on the one side you have 0, on the other side you have 1. Actually you have a shade, and this at 2.5% you're not very sure, and then as the number goes further, for example, if you have 1 head, it's less evidence against the null, and if you have 0 heads, it's more strong evidence, even though from the cutoff point of view both of them are the same, we make the same decision. But that's what it means to say that our reasoning is qualitative, not quantitative. Even though the action is 0 or 1, either we reject or we accept in the end, but it doesn't mean that the basis for the action is 0, 1. The basis for action is soft. It's not hard and firm and sharp. Now there's one very important issue that is not very well understood at all, and that's that we have asymmetric reasoning. When we reject the null hypothesis, it means that the null hypothesis is wrong. But when we accept the null hypothesis, it doesn't mean that the null hypothesis is true. So rejections are strong, but acceptance is weak. So we use language to accept, language to reflect this. We say that we reject the null hypothesis, or that we fail to reject the null hypothesis. The data that we see is not in conflict with the null hypothesis. This is what we say. This is because there is no unique null hypothesis. There are many others which are also compatible with the data. So actually this is a very serious problem, because although we say this, but in practice what happens is that when you accept the null hypothesis, you start thinking that it is true, and this is not correct reasoning, but it is often used. So because this is a tricky and subtle point and is not well understood in conventional literature, I will explain this from a number of different angles. So there is an Indian philosophy method which is called neti neti. It means that how do you search for the truth? You search by rejecting things. They say, oh, this thing, it cannot be true, so that's wrong. And this thing, it cannot be true, so this is wrong. So after rejecting a lot of things, you are supposed to arrive at the truth. Now, there are many, this method is quite deep, it's not very simple. It doesn't, there are many complicated things, and ultimately the list of possibilities is not finite, so even after crossing up a lot of things, you cannot arrive at one single alternative. So what you have to do is make a jump based on intuition. Now, what happens in statistics as you keep flipping coins is that the range of values which is compatible with the observations becomes smaller and smaller. If you have an infinite number of trials, then it becomes just one single number. So, if I flip a coin an infinite number of times, then the observed frequency will match exactly to the true probability. So this is the basis for the standard definition of probability, which is used in all conventional textbooks. That's called the frequency theory of probability, and what says is that if you take a number of trials n and you let that n go to infinity, then the observed frequency is the probability. This is called the definition. This definition is wrong. The reason this definition is wrong is because you can never do an infinite number of trials. So it's based on an impossible experiment. Now, with any finite number of trials, there is always a range of values of p. Although this range becomes narrow and narrower, it never becomes unique. So, as you increase the number of observations, the truth becomes clearer and clearer, in the sense that the set of possible values shrinks. The amount of inaccuracy in your estimate becomes smaller. So for any practical, real-world, real-life goal, you can usually achieve enough accuracy to realize that by a finite number of trials, although it may be very large sometimes. So things then depend, what you've got to do depends on your real-world application. How accurately do you need to know the value of p? It depends. There are many things that matter. If you are designing a dam and you are calculating the probability of water flows, then you need to know what is the probability that the water flow will exceed a certain value, which will cause the destruction of the dam. And so you have to make such calculations to design the appropriate strength which should last for 10 years or 20 years. And the probability should be so small that the event will occur only once in 100 years or something like that. Now, ideally you would like to make it 1 million years. But if you do that, that means that you have to make a very huge dam, and it's very expensive. So you have to be practical in the sense that you want to have a low probability of failure, but the lower you make it, the more expensive. So you have a trade-off between how. So these calculations have a very direct. Engineers make these calculations. Now there's a very famous quotation from Sherlock Holmes, who is supposed to be a Western wise guy, and he says that to Watson that when you eliminate the impossible, then whatever remains, however improbable, must be the truth. So he says that you have a list of possibilities, cross off everything which is impossible, and then the thing which remains must be true. This is completely wrong. This is not how it works. Even the Niti method is more sophisticated in this. Basically, the point is, this is what we learned from statistics, that when you eliminate something, it's not because it's impossible. It's because it's very unlikely. So, after you cut off a lot of things, then the next thing is that it never happens that there's only one thing left in the box that after all the explanations. There's always a large number of possible explanations, all of which are very improbable. So after you cross off a lot of things and then you come up with nothing which is plausible, you come up with something which is very improbable, then you have to go back, because those things were also very improbable. Now you are left with only one improbable explanation, and so then you have to say then you have to say that, okay, so this is impossible, but we crossed off some things which are maybe even more likely. So then you have to rethink about the things that you crossed off, because they were not impossible, they were just unlikely. Now, another way to think about this is with respect to Karl Popper, a famous philosopher of science. What happened in the West was that there was a conflict between religion and science in the West. Basically, Galileo is the famous example where he argued that the earth went around the sun, and the church forced him to take back this idea, or he would be burned. And some other scientists were actually burned at the stakes. So this created a great deal of hostility between science and religion in the West, and unfortunately we see a reflection of this whenever this is true to this day, that the scientists often feel very hostile towards religion, and they don't differentiate between Catholic religion and other religions, so they think all the religions are the same. So you find in books that there is a lot of prejudice and hostility against religion, which just comes from Western history. So one of the goals of Western philosophy became to prove that science is very superior and everything else is very inferior. So when we say knowledge, scientific knowledge is something wonderful, everything else is ridiculous. And this is called the philosophy of science. Now, in the 20th century, many theories were developed, and actually there was a famous theory which is called logical positivism, and this actually proved that science is the only type of knowledge, everything else is nonsense. Later on, people discovered that the basic ideas of logical positivism were wrong, and this was in the middle of the 20th century. Popper was one of the people who showed that the idea of logical positivism was wrong. It's a very complicated story, so I'll oversimplify and I'll say that one of the main problems is that science is based on induction. You see something happening and then you forecast that it will continue to happen. So you see that the sun rises every day, and suppose that you have observations for 1 billion years. Every day the sun has risen. So then you say, okay, there is a scientific law, every day the sun must rise, and this pattern will continue, but it need not. Tomorrow the sun could go nova, and then there is no sunrise anymore. So all scientific laws are like this, that you observe some pattern and you say, okay, this is pattern, this will continue. Now there was a lot of effort to prove that this must be a right way of thinking, but ultimately after a lot of effort it was decided this cannot be true, there is no way to prove induction because induction itself is not valid. It doesn't work. Sometimes it works, sometimes it doesn't, and there is no way to prove something which is not valid. So basically Karl Popper was the first to articulate. So this was a real shock in the sense that for the first time it became clear that science does not lead to the truth. It leads to a guess, and this guess could be proven wrong tomorrow if something happens which is outside the law. So for every day we watch the apple fall down, but suppose that tomorrow the apple starts to float up, then what happens to the law of gravity? And can we prove that tomorrow it will not float up? No, there is no way to prove it. All we have is that we have experience, but our experience does not make the opposite experience impossible. This was what the attempt was. The idea was that if I have experienced something all my life, then it must be true. It's not true. The example is that there is a chicken and every day the master gives it grain, so it says, oh, this is a very good guy, and one day the chicken is taken out and slaughtered. There is no experience in the past which leads to the prediction of this outcome, and this is very common. It happens all the time. So induction is not a valid principle, and if induction is not a valid principle, then all of science becomes called into question. So then there was an effort to find a new basis for science, and this was what was done by Karl Popper. He said that we can never prove theories. So then what distinguishes a good theory from a bad theory? If you cannot prove it, the idea is that a good theory has a proof and a bad theory has no proof. But this is not true. There is no theory which has a proof. So now how can we tell if something is good and something is bad? So Popper said that what happens is that you try to disprove theories. And if a theory survives a lot of attacks, then it means it's very strong. So this is what scientists do. They try to disprove theories, and if a theory has survived for a long time, then you can trust it until tomorrow. There is no guarantee of any theory, but the theories which have been attacked a lot and have survived are stronger than those which are newly made and have not been attacked. So this was his basic philosophy, and it's not really correct. There are many other issues that arise, but one main idea that you can never prove theories is correct. And so again, this shows the asymmetry that we are working with in statistics, that when I say that a theory is not rejected by the data, it doesn't mean it's true. It just means that I cannot reject it. So it has survived one trial, and maybe it will survive the next trial. But maybe, in fact, if you look at the history of science, you find that there's a huge number of theories which were proposed and survived for some time, and then they were rejected. This is basically in the mid-60s. Thomas Kuhn wrote a book called The Structure of Scientific Revolutions, and he said that our main idea about science is that it produces the accumulation of knowledge. You have some knowledge, and then you get more knowledge, and then you get more knowledge. But this is not how science really works when you look at the history. In fact, what happens is that you have a theory, and then more is added and more is added. But at some point, a revolution happens and everything is abandoned. You start in a new place. So this is very disturbing, because accumulation of knowledge means that we are approaching the truth, but the revolution means that okay, we have something, but the next revolution will destroy it all. So where is the truth, and how does it relate to scientific theories? Nobody knows at this point. Now, yes. Well, you see, everybody thought that Newton's theory of gravity was true, but then when Einstein came along with his relativity, then it became false. So it was true for a little while, and then it became false. This is not how logic works. Something is either true or it is false. It cannot be that something is true for a little while and then becomes false. Not about physical laws. So there is mathematical logic which has a certain type of proof that is similar to the process that we use for statistical inference. This is called the proof by contradiction, and what we do here is that we assume that something is true, and then we argue from this assumption, and we reach a contradiction. We reach something which is impossible. So when we reach a contradiction, we say, oh, I assumed that this was true, and that is the reason why I reached this contradiction. So this thing that I assumed true cannot be true, and it must be false. So this is called the method of proof by contradiction. And I will give an example. It's a very beautiful example. It's called the prime number theorem. I think it's due to some Archimedes or some ancient Greek. So basically, everybody knows that a prime is a number which can be factorized only by itself and 1. So the only factorization is that prime is equal to prime times 1. There is no other factorization. Every other number can always be factorized into primes, because when you factorize it, if something is not prime, then you can always break it down into prime factors. So ultimately, because not prime means that it has factors different from n and 1, so you can factorize it. So every non-prime can always be factored into primes. So you start with any number and you can factorize it into primes. So now the question arises, if you look at the number of primes, you look at list of primes, they become thinner. As you go up the numbers, the primes are fewer because you have a lot more factors coming in, and so a lot more things can be factorized as you go up. So the question is, does it stop or does it keep going till infinity? The list of 9, is it finite or is it infinite? So this seems like a very difficult question, because how can we go up and check every number until infinity? It's not possible. So this is handled by a proof by contradiction. So the proof goes as follows. Suppose we assume that the list of prime numbers stops at some point. So then we have a finite list, P1, P2 up to Pn, and this is the last prime. Multiply them all together and add 1. Now if you take this new number and divide it by a prime, then it will have a remainder of 1, because obviously the way it's constructed. So this number is not divisible by any one of the primes and we have all of the primes. So it means that this must be a new prime, because if you factorize it, none of the primes are the factors, and every number has a prime factorization. So this number cannot have any prime factor, and it cannot have any other factor. So it must be that n is equal to n times 1 is the only factorization, which means that it's prime. So we started with the idea that there is only a finite number of primes, and we got a contradiction. We found a new prime which was not on the list of the primes. So from this contradiction we understand that there is an infinite number of primes. The number of never stops. So this is proof by contradiction. Now, the way that the statistics works is that we make a null hypothesis, and then we reach a conclusion, and we say, oh, this conclusion is not impossible, but it is very unlikely. If it's very unlikely, that means that what we do is we reject the null hypothesis. Actually, we are not justified. This is a soft inference. It's possible that something is very unlikely, but it happened, and it can happen, it does happen in the real world, that we reach a conclusion and we say that the null hypothesis is rejected, but in fact it was true, and something very unusual happened. This is called a type 1 error, which can happen, and it has a probability of happening, and we will discuss that. Now, this is all philosophy. Now we come back to practical applications. Okay, so what we did is, these are Polio Rates, This is actual data from the number of cases of polio in Pakistan in 2013 is 93 officially recorded. In Nigeria it was 53, in Afghanistan it was 14, in Equatorial Guinea it was 0, Iraq it was 0, Cameroon it was 14, and so on. Now, we are thinking of modeling polio as a Poisson variable. It's a rare event, the probability is very low, and maybe it's independent. Actually, we will see later. Actually, I haven't proven it here, but this is not a good model because the independence is not valid. But that's something you can look at the data and see that the Poisson model doesn't work, and that's something that we need to learn. But for the moment, just to give the idea, we will assume that the Poisson model is valid. So every person has an independent chance of catching polio, and the rate is very small. The rate is cases per million. So you have a half a case per million population in Pakistan, 0.53. In Nigeria it's 0.33. In Somalia it's 20 cases per million. All of these are very, very low probabilities. So this is one condition of the Poisson, that the probability should be very low. And then we need the population. The population, I was just collecting this data last night, so I did not have the latest figures. So it's a little bit of a mismatch. This is polio in 2013, and the population figures I have are for 2011. And 2013 population figures should be available, but I couldn't find them in a hurry, so it shouldn't matter very much. The population should not have changed all that much. And anyway, we are going to illustrate the technique. So now the parameter of the Poisson distribution is lambda, which is equal to n times p. So I am going to illustrate a number of calculations. Suppose, to begin with, that the p is 1 per million, 1 case per million. This is different from the numbers that we see, but like in Syria it's 1.68, in Pakistan it's 0.53. So let's assume that overall average is 1, just to show how this kind of calculation goes. Later on I will make a more precise calculation. So now, suppose so that means that the p, the probability of polio, is 1 out of a million, 0.000001. It's actually one thing that you need to learn in order to deal with this kind of situation is the scientific notation. So 1 per million is 1e minus 6. It means 1 times 10 to the minus 6. It means that there are 6 zeros, and 1 divided by 1 followed by 6 zeros. 6 is the number of zeros. So 6 zeros is exactly 1 million. So this is the probability. The lambda parameter will be different for each country because the lambda is n times p. Lambda is the number of cases that you expect to see, actually, of the expected number. So if p is very low, n is very large, you multiply the two together, you get the number of cases that you would see on the average. So if you take NP for Pakistan, you multiply 1 divided by million by the population which is around 176 million, so you get 176. So in Pakistan, the cases that you would expect to see is 176.75. Now you can make this 177. As you will realize in statistics, and you have an appropriate level of accuracy, this rounding off will not make any difference because the decisions that we are making are qualitative, soft. Everything has a little bit of a fuzzy boundary, so you should not keep too many decimal places. It's just not relevant. But it's a question of judgment. You have to understand sometimes the decimal place matters, but usually it doesn't. Okay, so we expect to see 177 cases, but there were only 93. That's small. The question is it unusually small? Does it reject the null hypothesis? or is it possible that this is a chance variation, a little bit of a fluctuation, which is going away from the null hypothesis, so that's exactly right. Like in the heads case, 5 heads is the ideal, and if you have 8, is it too much? 9, is it too much? 10, is it too much? This is the question that we are trying to ask. So we should have seen 177, 93, is it too low, or is it within the range of normal variation? So this is the issue of what are the central values of a Poisson variable where the lambda is 177. What are the central 95% values? This is the question that we want to ask. And when we find the central values, then we can ask, is 93 inside these central values? Then it's normal. If it's outside, then it's unusual. So that's the question. So now there is a built-in function in Excel which is called Poisson, and it works just like your binomial dist function. So we call Poisson K, and then we give the parameter of the Poisson. This is just one parameter. In binomial you have n and p, so you give 2 parameters. Here we just, and then you use either true for cumulative or false for single value. So we are going to calculate the cumulative function, and I had to experiment with the numbers to find out. But here I look at, remember it's 177 that we are looking at. So at 170 you have 32% probability up to 170, and remaining 68% is above this value. So that's normal because 175 is the middle, and so up to the middle you usually have about half probability, and then there's a little bit more between 170 and 177. So as you go below, you get less and less probability. At 100 it's 0 to 6 decimal places. So 93 is even below that. So that means that 93 is very far from possible if the parameter is 176. In fact, where you start getting probability is around 123, which is 4 in 1 million. And then at 130 it's 1 in 10,000. At 140 now you get 2.4, no, this is not 2.4%, 0.24%. That is a quarter of 1% at 140. And then at 150, and these are cumulative probabilities, up to 150, all probabilities, not just the probability of the one outcome. So now you get 2.2%. Now this is the cutoff. This is coming close to the 2.5% cutoff that we are using. This is the 2.5 is a pragmatic number. Pragmatic means practical, and based on experience, that this is what you should do based on real world experience. It's not, it doesn't have a mathematical proof or a justification that we should use 25% to 2.5%. So after looking at this table, then I made another table with about 150 is where the cutoff should be. So I calculated the probability for 150, 151, 152, and I found that at 151 it is 0.026, so 2.6%. So that's over the cutoff. So basically that gives us a critical value between 150 and 151. 151 is within the central values and 150 is not. So this gives us a sharp cutoff. And that's important because when we are in a real world situation, you have to make a decision. You have to say yes or no. But it doesn't mean that you should say that this is the truth. I mean, this is a practical necessity. We have to make a decision. But at 150, we're not so sure. As it goes to 140, we become surer. At 130, we become even more sure. At 93, the probability is less than 1 in a trillion. So if the null hypothesis was really true, then we would see 93 cases only once in a trillion years. So this cannot be. So we can be pretty confident of rejecting the null. But if it was 150 cases, then once in 20 years it would happen, and so maybe it happened. And we can reject the null hypothesis, but we wouldn't feel very happy about this, that it's weak evidence, but we rejected it, but we keep in mind that maybe it's not false. So this is what I mean by soft and qualitative. In the same way, we can go up and calculate the upper critical value, and the upper critical value will occur at 97.5%, because we are keeping track of the cumulative from the, so 97.5% leaves 2.5% on the other side. So here we find that at 202 we are 97.1%, we are still below the critical value, but at 203 we are at 97.6%, so that goes above. So basically our upper critical value is between 202 and 203. So basically, if the null hypothesis that P equals 1 per million is true, and if the Poisson distribution is true, which happens not to be the case, then the range of values that is the central values are 151 to 203. These values are compatible with the null hypothesis of 1 per million. If you have value outside, below the lower critical or above, this is a conflict with the null hypothesis. So we start to think something is wrong. And as the numbers increase, we have more and stronger evidence against the null hypothesis. But there is no sharp cutoff. There is no point at which we say, okay, here, this is the final thing. It is true here and it's false there. There is no. It's gradual and it's shaded. Like most things in the real world, the boundary is not very well defined. There is a shade. At some point, you can say there is no conflict. So if you have like between 151 and 203, so if you have something like 170 cases, you can say, oh, this is very much what we would expect to see if the null hypothesis was true. And as it goes away, you say, oh, this becomes a little bit less and less likely. And at some point you start to suspect that maybe the null hypothesis is not true. And then at some point you become very strong in your belief that null hypothesis is not true. But it's all qualitative, it's not sharp and quantitative. Now, one very interesting thing which we have to do in statistics is to consider the reverse question. Instead of looking, so we created a null hypothesis and then we tested whether or not it was true. But actually, where did this null hypothesis come from? So this is what we are trying to answer now. We can ask, what is the null hypothesis for which we would not reject? So those are the null hypotheses which are compatible with the data. So it's we've already seen that lambda equals 176 is too high, because we would reject this. So we try to bring it down. What is the smallest value of lambda at which we would not reject lambda? So now this requires an inverted thinking. Now what we do is we look at Poisson of 93, lambda and the cumulative. So we vary the lambda and we ask, at what point does 93 reach 2.5%? As the lambda, at lambda equals 176, the Poisson of 93 lambda 1 is 1 in a trillion. It's impossible. As I bring the lambda closer to 93, the probability will increase. So at what point does it reach 2.5%? This is the exact critical boundary at which we would say that lambda is compatible with 93. So here you see, you start with the 115 as you and it's 1.9%. For larger values it will be even lower, because as you move further away from 93 on the top side, the probability of 93 will become smaller and smaller. Up to 93 will become smaller and smaller. As you move closer, it will become larger. So here in this table we see that at lambda equals 114, the probability of seeing 93, any value up to 93, cases less than or equal to 93, is 2.4%. As you move to 113, it's closer to 93, so the probability increases to 3%. So now 3% means that it's not in the lower critical values, because 3% is bigger than 2.5. So if lambda was 113, we would not reject the null hypothesis if we saw 93 cases, because it would be in the central values. If lambda was 114, then we would just barely reject the null hypothesis, because 93 probability is 2.46%, which is just a little bit lower than 2.5%, which is what we need to. So the lambda equals 114 or 113 is compatible with the null hypothesis, and 113 is compatible, 114 is not. So that's the boundary. In the same way, you can look on the other side, and basically at 75 you have 98%. Now you see at 75, at lambda equals 75, 93 is too big, and the probability is 98.1% up to 93. We are calculating the probability of 93 here, setting lambda equals 75, and so there is a 2%, or actually 1.9% probability of 93 and above. So it would be rejected. At 76, it's 97.47, and this is just barely the rejection point, 2.53%. At 77, now we are fine. It's 97%, and this is a 3% probability at 93 or above. So we would not reject at 77. It's close enough to 93. So basically that means that the range of possible values of lambda is 76 to 113.
Sir?
Yes.
Not clear about this point. Can you explain this?
Yeah. Well, basically, suppose we set lambda equal to 75, and so this means that we believe that the true expected number of cases in Pakistan is 75 according to the probability, which requires some conversion, which we will make. So then we saw 93 cases. This is larger than 75. Is it too large, and is it compatible with this idea that lambda equals 75? Well, we calculate what is the probability of seeing 93 or more observations of polio when the real true probability is only 75. Can we get such an excess? So we calculate the probability, and that's that's actually 1.9%, because 9810 is the probability up to 93. This number is, so it means that the probability is less than 2.5%. So we would reject the null hypothesis that lambda equals 75 if we saw 93 cases of polio. So in Pakistan, we reject the null hypothesis that lambda equals 75. Now we look at 76, it's closer. So now we have 2.53%. 2.53, yeah, exactly. So here we would not reject the null hypothesis, because it's more than 2.5%, and 2.5% is our boundary. And when we go to the next one, we would, it's now 3% probability for 93 and above, so we don't reject. So for values 76, 77, etc., we don't reject, and For 75 we reject the null hypothesis. So basically 75 is too far from 93 on the bottom side, and 114 is too far from 93 on the top side. So these values 76 to 113 are the ones for which 93 is possible, because it's close enough. Basically 93 has to be close to the expected value for it to be in conformity with it. If it is far, then it is not. These two are not compatible. If I hypothesize, if my null hypothesis is that the lambda is 150, but the actual value is 93, these two are not incompatible, because if the lambda is 150, we cannot see 93 cases. It's too low. So basically the question is one of determining exactly where the boundary is, and that's what we have done here. Now, so each value of lambda corresponds to a p, a probability. Lambda equals n, and so now we get some real information here, that we convert these lambdas 76 and 113 to p's. So we get 4.3 e to the minus 7. Basically we divide by p is equal to lambda divided by n. Yani lambda is equal to n times p, so p is equal to lambda divided by n. So we take the 76 and we divide by the population of Pakistan. 76 is the expected number of cases. Divide by the population of Pakistan to get the probability, and thus probability is 4.3 e to the minus 7. If I multiply by 100, this will become 430, and that's 2 zeros, so that will become e to the minus 9, which is a million exactly. So basically your probability is, the lower bound in the probability is 430 per million, and the upper bound is 640 per million. It's very small. No need to make a worldwide scare about this. This is the actual observed number of cases. So these are the probabilities. Of course, it turns out that the Poisson model is not the right model, so these are not reliable. But if we assume the Poisson model, then the range of probabilities for Pakistan is 430 per million and 640 per million. And this is a important piece of information that we learned from looking at 93 cases corresponds to this range of probabilities. This is actually called a confidence interval for the probabilities. So it's not like 1,000 per million, which would be 1 in 1,000. That's too high. It cannot be 1 in 1,000. And similarly, so now what we want to understand is that the process of statistical inference leads to soft and qualitative conclusions. These are not hard, sharp, accurate, precise. There is something which is called binary logic. Either something is true or something is false. In statistics, we don't have binary logic. We think this may be true, this may be false. I am quite convinced that this is true, and I am a little bit doubtful about the truth of this. Basically, it's like this. I mean, you have feelings and judgments, and experience will tell you, and you use your intuition. So, basically, for example, we created the cutoff value 4.3 e to the minus 7. So, when I say qualitative, it means that this is not a sharp bound. It could be 4.2, could be 4.4. And again, if we say 95%, why did we choose 95%? What about 96% or 94%? Yes, all of these are possible. And there is no harm in changing from 95 to 96. You have to change all the numbers and all the cutoffs. They will change slightly. So it's all possible. So it's just a pragmatic, practical idea. Basically what happens is that if we reject the null hypothesis, this is unusual, that puts us into trouble, because now we have to go and think, why is the null hypothesis false? And there can be many reasons, so we have to go out and explore. So basically we are looking around for unusual events, because an unusual event triggers that, oh, there's something wrong here, and you have to find. In a factory setting, this happens in the sense that you are monitoring for defects, and there is a certain number of defects which is normal. This actually happens in quality control. But sometimes you get, for example, 2 defects in a row. You say, oh, is this unusual? Should I go and investigate what's happening? Maybe there's something stuck in the machine, or should I not? So now, if you start investing everything which has low probability, then you will just have to waste a tremendous amount of time and effort. So you want to set a rule which is neither too sharp nor too soft. If you set your trigger too low, then you will be running out to the factory all the time. If you set it too high, then you will miss some real defects. So you have to set it in the right place. And the practical judgment is that 1 in 20 is the right number. If you set it to 1 in 10, 90% central values, and this has been suggested, you just get too many. 1 in 10 is, just as a matter of practical experience, you will have to start, you will mark too many things as unusual. So, and you will have to worry, oh, this is wrong, this is wrong, this is wrong, and it will happen too often. So you shouldn't do that. But in any particular concrete, precise situation, you might override. You might say that in this situation, even though this event is only 10% probability, I think it's unusual and I should investigate. This is a one-of-a-kind situation, it's very important, and so on. So depending on if something is happening routinely and you're doing it, then so it depends on very much on real-world considerations as to where you set the cutoff. So 95% is a good pragmatic compromise which works in general overall, but in any particular situation you might want to change that. Okay, now we go another example. I know that people like cricket here, so I was looking for data. Unfortunately, the only data I found last night was the data on Indian teams. So there are these 1, 2, 3, 4, 5, 6, 7, 8 Indian teams, and this is the one-day test matches in 2014. Maybe it's 2014. So you just look at the total number of runs in all the one-day test matches that they have played, and that was 2,427. In total it was 268.3, and so on. So this is the record for all of these teams. Now the question we want to consider is it true that everybody plays more or less the same, and this variation is just by chance? Or is it true that some people, as we all think, are really more skilled? Actually, it has been assessed that sometimes people are just lucky and they make a high score and people say, oh, he's playing very skillfully, but it is not true. So we have to distinguish between something which happened because the Kings 11 have a really high run rate, it's 9.05. The next highest is Chennai Super Kings, which is 8.35. So now is this difference between them? Maybe they are equal in quality, but Kings was very lucky this season, or maybe they are more skillful. How can we tell? So I'm going to transform this question into a question which I can assess by binary. Actually, binary methods, because you know the binary methods and you don't know the more advanced methods. When we teach the more advanced methods, we'll be able to actually do a more realistic model. But this model is not all that bad that we are going to do. So one thing we are going to do is we are going to assume that on every ball you can either score 1 or you can score 0, because that's what you need for the binomial model to work. Now actually you can do 1, 2, 4, 6, usually not 5, because so this is not binomial, then you have a sum of. So we in order to be able to apply the binomial, I want to just use 0 and 1. So now what happens when you score 4? Obviously it's not going to work, because you have 9 runs per over. If you do only 1 in every ball, then you don't get. So one trick I'm going to use is I'm going to say that every over has 12 balls, just to compensate for my other wrong assumption. So now if I have every over in 12 balls, then you can easily make 9 runs, and so there is no problem as long as a 0-1. So these 2 false assumptions I make, actually these are not serious. These approximations don't cause serious problems. There are other things which cause serious problems, but these are not the ones. Although it seems like we are making a big distortion to reality. But we can do the right thing, and we can model the real situation as it is, but it requires more complex methods. Okay, so what we do next is that, so what we do is we change the data and we multiply the number of overs by 12 to get the number of balls, and the score remains the same. So now the question we want to ask is, suppose that is this a sequence of binomial trials in which every ball by all the teams has the same probability P? So everyone has the same skill, all of the players have the same probability of hitting a 1 or a 0. There is a P probability, which is the chance of scoring 1, and there is 1 minus P, which is the chance of 0. And so the null hypothesis, everybody is all the same, and this is just random fluctuations. Actually, in this kind of analysis was done in baseball scores for the top 10 players in the USA, and they found that the null hypothesis that the 9 of them were the same could not be rejected, even though the scores were a bit different. But the one of them was an outlier, it was outside the norm. So one of them was really significantly better player. All the others were, according to the data, the same. The chance fluctuation. You see, if everybody plays and everybody is the same, somebody will score high, another person will score low, and there might be a big difference. But it will not be a reflection of skill, it will be a reflection of chance. So this is the issue that we are trying to explore. Okay, so there are going to be 2 methods I am going to use to show that actually the Kings 11 are real outliers. It's not a chance fluctuation. Okay, so suppose that the null hypothesis is true, that all of these people have exactly the same scores, exactly the same P's. Then what is the overall P? Well, what I did was I calculated the sum of all the runs for all the teams, and that is 16,950. And then I calculated all of the balls, and that's what I did was I added up all the overs and multiplied by 12. And so that turns out to be 25,324.8, which I am going to turn into 25,325. So that's the number of balls that was played by all the teams, because I am now considering in the null hypothesis that everybody is the same, so I just merge everything. So the total number of runs was 16,950, total number of balls was 25,000. So what's the run rate? What's the P? Well, the observed frequency is 16,950 divided by 25,000, which is exactly this. If you see, it's 66930, and that's a 67%. So the observed probability of success is 67%. So when you the probability P that you hit the ball and you score 1 is 67%, and 33% is the probability that you score 0, you don't hit. So this is the overall average for everybody. So let's see. So this is the binomial that I'm going to take. That the binomial is P is going to be 67%. Now in the first team, the Kings 11, this is 12 times the number of overs, which is 3,220. So that was the total number of balls that they had to play, and they scored 2427. And if you take the ratio 2427 divided by 3220, that's 75.373%. Just divide 2427 by the number of runs by the number of balls played.
Sir?
Yes.
How did we get 3220?
Oh, that's 12 times 268.3.
12 times 2.
Yeah, you can see the formula up on the top. It's 12 times C11 over here. It means that, you see, the total overs was 268.3,
Right.
and I'm assuming every over has 12 balls, so I just multiply. And then this 0.7573, this is the ratio, 2427 divided by 3220. Okay? So now 75.3% success rate is higher than 67%, but not that much higher. Maybe it was just chance. So to answer that question, I have to look at, I don't know. Oh, this is a different score. Okay. So let's go back to here. So we look at the binomial dist function, and we look at, actually this is the thing that you look at. Binomial dist 2427, this is the k, and 3220 is the number of runs n, and we set the p to the null hypothesis 0.67, and we calculate the cumulative probability. Well, this turns out to be 1.00000000 and so on. And it's just the probability of being 2427 and above is like 1 in a trillion or less. This is too high. Let me show you in the Excel. Okay, so I'm going to write this over here. Equals binomial dist of 2300, comma, n is 3220. That's the number of balls. P is 0.67, and I want the cumulative. So you see, this is 0.999 up to so many decimal places, and this is at 2300. So the probability of scoring up to 2300 is almost 1. There is only a 1 in a trillion chance of being above that value. And 2300 is a lot smaller than 2427. So you simply can't reach. So at 0.67, if the probability of scoring a 1 is 0.67 and you have to play 3220 balls, chances of scoring 2427 are just less than 1 in a trillion. You can, even 300 is not possible. So 2300 is not possible, and you have to go much lower. In fact, I have done the calculation, and basically 2209 runs is what you reach 97.5%. You just work through the numbers and you find out at what point do you reach 97 point. So basically the probability of being above, so the upper critical value is 2209 or 2210. So 2210 you have 22.5% probability. So basically, if you have a 67% chance of scoring one run and you play 3220 balls, the maximum you will score is 2210 in 19 out of 20 cases. This is 95%. In one case you will go higher, but 19 out of 20. So with 95% confidence we can say that a team which has 67% probability of scoring one will not score more than 2210. But now the Kings 11 scored 2400. So it cannot be due to just chance fluctuation, just luck. There is another way we can reach the same conclusion. We apply the scoring. We look at the probability of Kings 11 themselves. They have a score of 2427 in 3220 balls. So the observed frequency is 0.754. This is just the ratio of 2427 to 3220. So now we ask, what is the minimum amount of runs they can score? And this is the average that they will be scoring, 2427. What will they do on an unlucky day? So we apply, we calculate the P, and the P should be about 75.4% because the law of large numbers, 3220 is a big number. So we can say that the observed frequency should be close to the true probability. So just set it to set P equal to 75%. Now, what is the range of normal variation at P equals 75.4%? So if some team has 75.4% probability of hitting a 1 and it plays 3222 runs, how much will it score? What is the central set of values? So I look at this and I say that at 2350, which is less than 2427, and 2427 is the expected number, right? So 2350 is less. The probability is 0.0085, very small. At 2360, you get 0.03. At 70, you get 0.09. This is about 1%. 80, you get 2.6%. Okay, so now we are at the critical value. So basically, because I know it's between 70 and 80, then I make a second table which goes by digits. I go 2, 3, 7, 5, 7, 6, 7, 7, 7, 8, 7, 9, and I see that at 7, 9 you are at 24.4%. At 80 you are above. You are at 2.6%. At 79 you are at 2.4%. So the critical value is 2379 to 2380. So when you are scoring 2427, then the lowest you can go by bad luck is at 2379 to 2380. So smaller than that is unusual. So the central values for Kings 11 is between, in this set of ours, is between 2380 runs, and there is an upper value. I didn't calculate it because we don't need it for this purpose. So basically, if you look at the frequency, 2379 over 3220 is 73.9%. This is about 1.5% lower than the 75% which was observed. Means that about 1.5% fluctuation is possible by luck, not more than that. So now you look at the next highest score. The next highest score is Chennai, and it has an observed frequency of 69.6%. It scored 22.72 in 3264 balls. So this is their average. If they were if this was an unlucky day for them, maybe their true P would be 1.5% higher that would be 71.1%. This is the maximum. About 1.5% is about the maximum fluctuation you can have. So, even if they were very unlucky, 22-72 was not actually a good reflection of their performance. The good reflection would be at 71.5%. This is the highest you can change within the 95% bound. So this is still smaller than 73.9%. Means that there is a significant difference between the performance of King's 11 and the performance of the Chennai team. So we can say that King's 11 is better than the Chennai team due to skill. They don't have the same probability of scoring 1. They can't have the same probability. Okay, now we come to the basically this conclusion is based on several assumptions, and these assumptions are not valid. One of them is the assumption that the P is the same for all balls for any one team. Actually, some people are better at hitting, and so they will have a higher P. Some people are less, they will have a lower P. And you can put in all of these complications, and people do. And you so you estimate P separately for each player, and then you can still do the same thing. But this is actually, it turns out it doesn't make much difference. I mean, for this particular exercise, this significant difference will remain even after you put in all of the complications. And so we come to the conclusion. So now, you see, always in statistics, the way I am trying to teach it, you have to look at the real world and you have to look at the statistics. So the statistics is a pointer to a real world. So now we say that, okay, the King's 11 is better than the Chennai team. And so, why is this so? Well, there are many possibilities, but you have to know about the real world. So you can say that probably they have better players. If you calculate the skills for the players on that team and the skills for the player on the other team, then you will find, you can, just like we can distinguish between performance of one team and another team, we can do the same calculation for one player of this team and the other player based on their records, and we can assess, do they have the same probability or do they not? And we can come up with the conclusion that maybe the batters in this team are better. Or it could be other factors as well. We can calculate whether or not there is a home ground advantage. We can calculate whether or not there are some basically, to find out why the null hypothesis fails, you have to look at the real world. Is there a magnet? Is the coin twisted? So basically the statistics gives you a clue, and then you have to investigate in the real world, follow up, and the investigation will depend on the exact situation. If it's cricket, you will investigate different types of things. If it's the same kind of thing works when you are trying two different drugs and you ask which drug is more effective, and then you can assess, cure rate from this one is like this, cure rate from the other one is like this. Is this significantly better or is this just about the same? So if it's significantly better, then you can ask why this is better and many other types of questions. But all of these things have to do with the real world. You can't do statistics all alone just by looking at numbers. You have to put it into the real world. Okay, so that's all for today.